These are two 7-segment displays that I made in Yeeps Hide and Seek. And if you remember my last video, I said that I'd make a 2-digit display next. So, well, if you look behind me, I added a good bit.
So here's a quick recap if you didn't watch that video or don't remember. Like I just said, I made these two displays in Yeeps Hide and Seek that are able to show numbers 0 through 9 using these four buttons to change the displays. If we're going to have this be 2-digit, we need the displays to show all numbers 0 through 99. So it's going to need a bit of an upgrade. Because these four buttons can only make 16 different combinations, we're going to need a bit more than that to reach 99. After a bit of adding, I found that 7 buttons would be the best option because it has 128 different combinations. Although it's a bit too large, if I use 6 buttons I'd only be able to go up to 64. And I'd rather have more than less combinations. And now, with there being over 100 button combinations, each showing a binary number, I think that is a good segue to explain our next section, how to read binary. So my displays use binary inputs to show numbers. And with this display, using 127 different inputs, we're going to need a faster way to read binary. Let's say if you see this number. If I asked you what it is, you would hopefully immediately identify it as 153, and can imagine its value. Okay, good. Now here's another number. Can you tell me what its value is? Unless you know how to read binary, you would have no perception of how much it's worth. We need a way to identify these numbers quickly like we can in base 10. Now you could use the method from my last video and count on your fingers until you reach this configuration of 1s and 0s. But I'm not even going to try to make an animation for this because counting to 9 took me a couple hours to animate. Doing this would take forever. So here is how you read binary. So what you do is you multiply each digit by the number 2 to the power of the number place of that digit, minus 1, and add all the products together. That is a mouthful, so let me show you an example. So under each digit, we have a 2, and each of those 2's have an exponent. The exponent starts at 0, and as you go to the left, each digit, you add 1 to it. So under the first digit, we have a 2 to the 0 power. So what we do is take 2 to the 0 power and get 1, because for some strange reason I still don't fully understand, anything to the 0 power is 1. So now you multiply the 1 we got with the first digit. And the first digit of the binary number is 1. So 1 times 1 is 1. Then we look at the next digit. And under that digit we have a 2 to the first power, which would be 2, but because we would multiply it by the second digit, which is 0, anything times 0 is going to be 0. So we can just ignore this one. Because of this, we can also skip the next few because all those digits are also 0. Under the fifth digit, though, where we have another 1, we have a 2 to the fourth power, which is 16. And 16 times the digit, which is 1, is 16. Then we skip the sixth digit and go to the seventh, because there we have another 1. Under the seventh digit, we have a 2 to the sixth power. 2 to the sixth power is 64, and 64 times the digit, which is 1, is just 64. Then finally, we add all the numbers together, being 1, 16, and 64, which adds to our final number of 81. So this binary number is equal to 81. I think an easier way to think of this is for each digit you double the value of the last one, and add all the values together of the digits with 1. So first we start off with 1 under the first digit, and then next you double it, so it becomes 2, and then double it again, so the third digit gets a 4, and then double it again, so the fourth digit gets an 8, until you eventually reach 64, or all your digits are filled. Finally, you add all the numbers together with a 1 in the digit above them. So again, we're adding a 1, 16, and 64, making 81. It's essentially the same concept, just without thinking about it with exponents. So that is how you can read large binary numbers pretty quickly. If you need to read any larger numbers, the process is the same. Now that we have the inputs to show all the numbers we need, and know how to read binary, we now need the displays to show the numbers we enter. Right now the displays each take the binary numbers 0 through 9, or in binary 000 to 1001. So we need a way to split the larger binary numbers into two smaller numbers for each display. Let me show you what I mean. If we had this binary number that is equal to 74, we're going to need to output a 7 to the tens digit and a 4 to the ones digit to make the final number. So we need a way to split this number into two smaller ones representing each digit. This output is called BCD, or binary coded decimal, and we need a way to convert binary into its BCD form. The method I will be using to convert binary to BCD is called a double-double, and it works like this. So I just got a random binary number on the right with two columns representing each display to the left, one being the tens column and one being the ones column. So how the double-double works is we slide the binary number to the left one digit and check if there's number 5 or greater in either column. So after we slide this number to the left one, there is a 1 in the ones column and nothing in the tens column. So neither are 5 or greater. Next we slide it again, and now we have a 2 in the ones column, but again that's not 5 or greater. Now though, if we slide it over to the right one more time, there is now a 5 in the ones column, and because 5 is 5 or greater, we add 3 to the 5, making it 8. After adding the 3, you again slide to the left and until there's another 5 or greater in the ones or tens column, which after sliding to the left 3 more times, we end up with a 7 in the ones column. So we have to add 3 to the 7, making it 10. And when you add these numbers, make sure not to change anything outside the column you're adding to. Finally, we do one more slide, leaving us with a 9 in the tens place and a 4 in the ones place. So that makes this number 94. And if we check that with the original number using our reading method we just learned, we're adding together a 2, 4, 8, 16, and 64, making the final number 94, exactly what we got from our double-double. I am going to be completely honest, I have no idea why this double-double works or how anyone thought of this in the first place, because this design is really simplified and easy compared to other possible methods. So now we just need to get our 7-digit input in Yeeps and put it through a double-double. Because I did the truth tables and math of it last video, I will quickly gloss over that part because it's the same. This would though be the truth table for the double-double. It only has 4 inputs on the left and 4 outputs on the right. And the 4 inputs and outputs are the same until you reach number 5 or greater, where the output is 3 more than the input. So essentially just adds 3 to the numbers 5 or greater.
So here is an in-game dabble check. So here we have the 4 inputs, A, B, C, and D, and on this side we have the 4 outputs, A, B, C, and D. So this chip works the exact same way as it did with the truth table, where if the number is 5 or greater, it will add 3 to the output. Otherwise, the input will be the exact same as the output.
Now this addition is not all we need for the double-double, because all it does is check and add. So I will refer to these as dabbles, since they are not the final double-double. So now at the final steps, all we need to do is put one of these dabbles in every spot where it is possible for there to be a number 5 or greater. I will make a quick diagram of how it is to be made in game. So each of the letters at the top represent one of the digits of our input when we are in game. So there's 7 of them, with A being the largest and G being the smallest digit. So the first dabble will be given to the first 3 digits of our binary number, because 3 digits are the smallest number of digits you can have to make a number that is 5 or greater. So there's no point in checking the first 2 digits on their own because they can never be 5 or greater. After those 2 inputs are put through that dabble, we then need to shift all of our outputs to the left. And instead of moving the wires to the left, I actually move the dabbles to the right, just so that the wiring doesn't shift as we continue down. So now here's where the next dabble will go. Now if you noticed one of our wires on the left no longer has anywhere to plug into, I will get back to that one later. Again, we make another dabble to the right and leaving one of the wires out to the left. We do that one more time until we have 3 wires with no ports to plug into on the left. Now that there are 3 wires that can be 5 or greater, we're going to plug them into a separate dabble, and this is equivalent to us checking if the tens place will be 5 or greater in our example. Now we will still have to make a dabble for the other 4 wires, but now finally we just have to plug all of these outputs into our 7-segment displays. So the first 4 on the right will go to the ones digit, the next 4 will go to the tens digit, and we do have one left on the left side. And that is because if you remember from the beginning of this video, our numbers can go up to 127. So this last one would plug into the hundreds digit if we had one. Just like in my last video, I do want to say again, if you want to look more into these things, there are great resources online, and if you would like to learn all the technical aspects. But now, with the design finished, all that is left is to build it. And while this is building, I want to talk about how I was able to condense these designs, because I did a lot to try to use as little logic gates as possible. That is the reason I have 3 different iterations of my 7-segment display, because I struggle with making it a reasonably small size. I also challenge myself to not use transmitters and receivers in this design, and yes, I do use them for the buttons, but you could easily run some wires from the outputs to where the receivers are. One of the big things I did to condense these designs is I reused some of the outputs from other parts of the design, so I wouldn't have to remake the same part twice. And after I learned to do this, it made making this double dabble much easier, so I didn't have to iterate so many designs. Also, side note, I was actually on my last day of building and it was really difficult because it was April 1st. And if you don't know, the developers had an April Fool's joke, and everyone grew legs. So I had to completely relearn the movement. So now I have a greater appreciation of not having legs. Wait a minute, but now I think it's time I show you the final design.
Okay. Final showing, take 2. So here it is, my final Yeeps 2-digit, technically 3-digit now display. Actually, what I did is, remember that hundreds digit wire that was extra? I wired an extra one to it. It is pretty pasted on right now, but I think it will look better when we fill all this in. So now it can show numbers up to 127 instead of just 99. So now the displays can go up to 127 with that extra one there. So I think it's time I show you. This is 0, so we can still show 1-digit numbers like 4. But now, not only can you show 4, you can show numbers like 16, and even higher than that, we can go up to 64. One thing I don't like about these displays is they are pretty slow. And that is because of how many wires and double dabbles I have on the back, or dabbles I have on the back. So this number is 112. So technically a 3-digit display in Yeeps Hide and Seek.
Before I end this video, I will say these displays are not super fast, but I think if you optimize them for a specific game, I'm sure you could speed them up, because in this state, they would not make a very good game clock. In my next video, I plan to finally build the final addition calculator, though this may take a while since I have to build 2 more of these displays and the addition. I do though plan to make a short in between to break up the silence. There is one more problem that I have not mentioned though, and that is that with only one display, Yeeps has already given me the too many wires warning, which if you don't know, Yeeps struggles to handle a lot of wiring, so it gives me a warning if there are too many. So I guess the only way to know if it'll work in the end is by continuing. If you do want to, I would definitely encourage you to learn more about these displays further yourself, but if you watched this far in the video, I'd like to thank you and remind you to keep learning.